The limits of sequences satisfy some of the same rules as limits for functions. And a summary of these can be found in Theorem 9.2, Properties of Limits of Sequences. So we see the first condition here is that the limit of the sequence a sub n exists and is equal to L, and the limit of the sequence b sub n exists and is equal to K. So very important here is that the limits exist. The first property is the scalar multiple property, and that tells you that when you have a scalar multiple inside a limit, you can bring it outside the limit. Just note that this is, if you rewrite this in terms of the limit, right? So rewrite this as limit as n goes to infinity of c times a sub n. According to this theorem, that is equal to c times L, and L is the limit of a sub n as n goes to infinity. In other words, a constant multiple can be pulled outside the limit. The second property is the sum or difference property, and that states that the limit of a sum is the sum of the limits, or the limit of a difference is the difference of the limits. So I'll just write down the first one. The limit of a sum or difference equals the sum or difference of the limits. Furthermore, the limit of a product is the product of the limits. Limit of a product is the product of the limits. And again, this holds as long as the limits exist. So you may have some cases where the limit of the product exists, but it's not equal to the limit of the it's not equal to the product of the limits because one of the limits might not exist. So something like 1 over n times n. Also, the quotient, the limit of a quotient is the quotient of the limits. Limit of a quotient is the quotient of the limits. Provided that the limit on the bottom is not equal to 0. Now, a very important theorem that we sometimes have to apply to figure out what a limit is the squeeze theorem for sequences. So if you have two sequences, a sub n and b sub n, that both have the same limit L, and there exists an integer capital N such that the sequence c sub n is squeezed in between a sub n and b sub n for all little n greater than capital N, then the limit of the sequence c sub n also equals the limit of the sequences a sub n and b sub n, namely L. So let's take a look at an example how we apply that. So in this example, we're asked to find the limit of the sequence a sub n defined by -1 to the power n times 1 over n factorial. So the first thing is we need to realize that we cannot just use the theorem we used before and change this into a function f of x, because we don't know what f of what x factorial is if x is not a natural number. So first, what we should note is that n factorial grows very fast, and it grows much faster than 2 to the power n. So n factorial is greater than 2 to the power n if n is greater than or equal to 4. And so I'll show that over here. So let's take a look at n factorial. I'm going to start with the 1, and I'm going to write it as 1 times 2 times 3 times 4 times 5 times 6 times, and then all the way up to n minus 1 times n, right? And 2 to the power n is equal to 2 times 2 times 2 times 2. Let me align that a little bit better with the n factorial on the top. So that's 2 times 2 times 2 times 2 times 2 times 2, and that never changes. So that's 2 times 2. So now let's take a look at those first 4 terms, right? So if we look at the first 4 factors, I should say. So 1 times 2 times 3 times 4, that is 24. And then we have the first 4 factors of 2 to the power n, that is 16. Now, so if you rewrite this, right, this is equal to, you rewrite the top, you see that that is equal to 24, and then times 5 times 6 times, and then all the way up to n minus 1 times n. And the bottom, we have 16, and then times 2 times 2 times 2 times 2. Now we can clearly see that every factor here in the top is greater than every factor on the bottom. So what we see here is that n factorial is greater than 2 to the power n if n is greater than or equal to 4. Now, because n factorial is greater than 2 to the power n, when you take the reciprocal, 1 over n factorial, that is smaller than the reciprocal of 2 to the power n. Right, so that is a conclusion that we can make, that 1 over n factorial is less than 1 over 2 to the power n. Okay, so let's start out with that observation. So we have 1 over n factorial, and that is less than 1 over 2 to the power n. But our limit has a negative 1 to the power n. So what happens when we introduce that negative 1 to the power n? That is not a problem for this inequality, because if you make this negative, it's certainly less than this positive number. And the worst this can be is positive 1. And so then you just have this inequality here. However, on the other side, we can say that this is always greater than negative 1 over 2 to the power n. And so now we have a squeeze, right? This is our sequence a sub n, and then we have 2 sequences that that this a sub n is squeezed in between. Now, what we'd like to show is that the limit of this sequence and the limit of that sequence is the same, and so it really squeezes this sequence here. So what we're going to do is we're going to take the limit on all three sides here, right? So we're going to take the limit as n goes to infinity of, and then we have negative 1 over 2 to the power n, and then that is less than, and then we take the limit of the middle part, limit as n goes to infinity of negative 1 to the power n times 1 over n factorial, and that is less than, and then we take the limit of the right hand side, limit as n goes to infinity of 1 over 2 to the power n. Okay, now you can, if you want to, now replace the n by an x and then see what happens when x goes to infinity. And you'll see that basically when you plug in infinity, you get 1 over infinity. And so that limit is 0. So we have 0 here. And the same holds true here. You get negative 1 over infinity is negative 0, but negative 0 is equal to 0. Oh, and one thing that I should change is once we take the limits, these strict inequalities become equalities or inequalities that can also equal. So we have 0 is less than or equal to the limit as n goes to infinity of a sub n, right? This is our a sub n. And that is less than or equal to 0. So the conclusion here is that the limit as n goes to infinity of a sub n equals 0. So visually, you can represent it as follows. The dotted line here is our sequence negative 1 to the power n over n factorial. So this is your sequence a sub n right here. And it's squeezed in between the following two sequences, the negative 1 over 2 to the power n on the bottom and the 1 over 2 to the power n on top. And you see in the beginning, it is not squeezed in between, but once you get to you see 1, 2, 3, 4. Right at the fourth term, it is squeezed in between, and then ever after.